Okay. Let me just talk a bit about, so there are no infinite tensor products, but there are infinite direct sums. And so I'll just, they can be defined, yeah, for any. Let's define them for ordered. I'm not sure. Okay, so let R be a commutative ring with unity, and E is some set, an infinite set maybe. Okay, a set may be infinite. And we have a family of AI for I in BK is a family of R modules. And we define the direct sum, so A, I in I, the direct sum of these modules to be the module with elements, with elements, so E, why I put A anyway? I usually use V, but this time I used A. So A I1 plus AYN, where n is an integer and I1, IN are indices, and AI1 is in big AI1, and so AIN is in big AN. And with pointwise scalar multiplication, so if we multiply this by lambda, or components multiply by lambda, pointwise scalar multiplication, and addition of common components. So I'm not writing this down, but if I have another such kind of sum, I only add, so if I have A3 and then B3, I add them. If I have A3 plus B3 and then A3 plus A4 and then A8 plus A9, I just form the formal sum of them. And an example that we discussed, but haven't used that terminology. So example for that is the following. So first of all, so R be an R module. Sorry, commutative ring with unity. And then we have that the set of polynomials is the following direct sum, is the direct sum e from 0 to infinity of the span of x to the eighth power. So this is the direct sum of this kind here. So this is like R. So this is A0 in R plus A1x, A1 in R, and so on. So polynomial is a direct sum of one-dimensional spaces, which are the polynomials of fixed degree. So we have, let's say, an x to the n power, and so on. So this sum goes to infinity. Okay. Now, while I'm doing this definition, in order to define the tensor algebra, but before defining the tensor algebra, let's define what an algebra is. So an algebra is structure that is studied by abstract algebra. Okay, can I? So algebra. Algebras. So definition. Let R be a commutative ring with unity. V be a set and plus is from V times V to R to V, sorry. Let's say this is multiplication is from V times V to R, and scalar multiplication is from R times V to V. And we say that V with addition, so it has addition, but it gives zero and negation, but I don't try them. Scalar multiplication, so multiplication and scalar multiplication is an algebra, R-algebra, or algebra over R, I use this term, if, so first of all, V with addition and scalar multiplication is a group, is a module. So we start from a module and not another operation. Or we can start with some kind of ring and not scalar multiplication. The two, both directions can be made. So this is an R module and star distributes over V. Over plus. i.e. for all, let's say, x, y, z in V, x plus y star z is x times z plus y times z, and x times y plus z equals x times y plus x times z. We have two distributive properties. So there are three main operations: addition, multiplication. So rings had addition and multiplication. Modules have addition and scalar multiplication, and algebra has both of them. If we have associative property, so if star is associative unito, so it has a unit, or commutative. Oh, sorry, I forgot one thing. And also, we have that for any, so here I also have lambda in R. Lambda and lambda times x. So we have multiplication in the intrinsic multiplication, and then with scalar is the same as lambda times x times y. So we have like some kind of associativity. So I forgot that. Okay, so if star is associative unito means that it has a unit, that when you multiply it is the same. Unito or commutative, we say the same for the algebra. Okay. Usually people study, when talking about this kind of algebras that we're going to discuss, they're usually associative, but in discrete, in mesh calculus, we have coproduct that is not associative, so not always. And also I would some note, Lie algebras do not have need. I will not talk at all about Lie algebras, but just to mention, Lie algebras don't have any of these three properties. They have two other properties. And have any of these three properties. So
by three properties you mean Euler?
Yes.
No.
Yes. It's okay. So let me give some example. The polynomial algebra. So let R be a commutative ring with unity. Then Rx is, so we have multiplication of polynomials, multiplication of polynomial with a scalar, and addition of polynomials. Rx is, so the polynomial algebra is associative unito, so one is the unit. The constant polynomial one is the unit, as usual, and commutative. And does anybody know if I remove commutativity, what kind of algebra will get similar to the polynomial algebra? I'll get the tensor algebra. Well, not because this is of one-dimensional space and the tensor algebra is commutative there as well. But if I have polynomials of two variables, so R, X, Y are so polynomials of two variables of n variables are also have these properties. So if I remove the condition for commutativity, I will get the tensor algebra. Oh, sorry, and Rx and is infinite dimensional. Okay. So start with commutative link with unity. V be some vectors, be some module, be R module. And take some the tensor algebra of V is the smallest so associative and unital algebra or also the free such algebra, the smallest. Some people sometimes more maybe more rigorously is the free algebra, the free associative unital algebra containing. So this is the smallest one containing V. Okay, so if we have so the elements of tensor algebra V, this algebra T star, sorry, T of V are of the form linear combinations of things of that nature. So they are of elements of the form. So we start V1 times V2 Vn. If we add such things, if they have common factors, they will add up. If we multiply them by say W1 to Wm, it just goes on the right. So these are some kind of abstract entities, and we don't have commutativity. We only have associativity. So we can remove brackets, but we cannot interchange. So we have that the tensor algebra of V is as a vector space. As a vector space. So it has three operations: addition, multiplication, scalar multiplication. If we discard the scalar multiplication as a vector, as a R module, as an R module. Oh, sorry. No, this will be a bit wrong. Or not. Yes, it's an R module. No. Okay. If V is finite dimensional, with basis E1 to En, then T of V is infinite dimensional with basis the following. So I have 0 tensors, so 0 tensors. One of the 0 tensors. One tensors. These are E1, En. These are only the bases, not all the vectors. Two tensors are E1, E1, E1 times En, and then we have En times E1, En times En. So we have that, yeah, so, and so on. So therefore, the T of V is the following infinite direct sum. It's I from 0 to infinity of T I of V, where these are finite. So Ti of V is I to the power of N. Because there, for example, 3 tensors, we have to choose 3 of them. So basis of Tyv is I1 times EIN, where all of them are in this interval. No, maybe J. So if we had only symmetric ones like polynomials, then E1, E2, and E2, E1 be the same. But for the general tensor algebra, they are different. Okay. Now, we have the following properties. So note that if let's say x is in ty and y is in tj of v, then where does x tensor product with I live? So Ti is the space of O that have exactly Y components in them. So if I multiply thing with I components with thing with J components, what I get? No, I have, for example, a 2 tensor E2 times E4, and then 3 tensor E1 times E5 times E7. When I multiply them, what's its dimension? Like if I multiply monomial of degree 2 and monomial of degree 3, what's the degree of the monomial?
6.
I multiply x squared times x third. Yeah, yeah. So this is t of y plus g. So we write x is the degree of x is I, or x is monomial of degree y. X is monomial, but non-commutative monomial, like monomial of degree. Let's put it in brackets. So, and algebras that have that decomposition and that property are called graded algebras. And graded algebras are needed to define the exterior algebra. So let R be an R module. Oh, commutative ring with unity. A be an algebra, an R-algebra that has the decomposition of the form A is a direct sum of from 0 to infinity. This sum may be finite if at some point all the module becomes 0, an infinite sum becomes finite sum. Like in infinite sequence, if you have from some point to infinity all the terms are 0, the sum becomes finite. So this is the sum. And for any homogeneous it's not in brackets, homogeneous x in AI and y in IJ x times y is in ai plus j. So if we have this property, we say that A is a graded algebra. Okay. So examples, let's just write this. So for now we have two examples, polynomials and tensors. So polynomial and tensor algebras. And they are graded by the degree of their objects. So polynomials of degree 5 multiplied by polynomials of degree 6 is polynomial of degree 11. And tensor algebras that are graded by degrees of their elements, degrees of their elements, of their monomials, let's say. Okay.
I think it would be good to give a specific small example of graded tensor.
Okay, okay, so the example,
Gradability of the tensor.
let's say V is R squared and consider T of V. So, let's say X is okay, and E1 is 1, 0, and E2 is 0, 1 to fix the basis. Doesn't matter what the basis is. So X is 2 times E1 times E1 minus 3 times E1 times E2. And Y is 2 times, okay, E1 times E2 times E1 minus or plus 2 times E. So this is into T2, this is will be E1 times E1. This is in T3. And when we multiply them, so X multiplied by Y, it's just multiplication and this distributive flow. So we have 2 times E1 times E1 times E1 times E2 times E1 plus 4 times this by this. So I call it, let's call it T to the 5th power. It's E1, 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 E1. This is E1 to the 5th power. And this, then I have minus 3 times E1 times E2. So there are E1 times E2 times E1 times E2 times E1. And then I have this by this. So this is minus 6 times E1 times E2. And then again, I could write this like this, but I could write it E1 to the third power. If you want, you can write it in full, but it's 5 times C1 multiply. And so this has 5 components. This has 5. So all of them have five components. So they're in the space of all things with 5 components. So this is in T5 of V. Is it better now? Okay.
I think some things are very different for everyone. This clarifies that each of these is a new object.
Yeah.
So E1 is an object, E2 is an object. Well, object, two different vectors at the basis, but then E1 cross E1 is a completely different object. It is a different.
Yes. Well, I illustrated.
Each of these terms is a completely different object.
Yeah. Okay. Yeah. I illustrated.
No. Yeah. I mean, one cross is a different thing from having 2 crosses.
Yeah.
5 crosses. Or how many we have?
Here we have 5.
4.
This with this are
It's 5.
5. Yeah. Maybe I should. Oh, I just have 4 here. Why didn't you tell me that I have 4? 2 by 2 is 4. Okay. So yeah, if it was commutative, this will be E1 to the third and E2 to the second, to the squared. But it's not commutative, so we cannot. But more interesting for us are anti-commutative, the so-called alternating algebra. Let's just give some before that. Yes. A very small proposition, and because I will need it, let R be not any, but they're equivalent. Let R be a link. And that has the following property with the following property. For all R in R, R squared equals 0. Then, so we have, this is alternating property. Then, so I'll use this as definition in the future. Then R, for any R and S in R times S plus S times L is 0, or RS is minus SR. And the proof is very easy. So 0 is, so let R and S are in R, then 0 is R plus S squared, R plus S times R plus S. By definition, because any element to the by itself multiplied is 0. And this is R times R plus R times S plus S times R plus S times S. This is 0, and this is 0. So this is 0, and this is 0. So the whole thing is RS plus SR. And this is what we wanted to prove. So we have alternating means anti-commutative. Anti-commutative. anti-commutative because we change sign. So SR equals minus RS. And this is alternating ring. Now let's talk about alternating algebra. Let R be a commutative ring with unity, and A be a graded algebra, graded R-algebra. So A is I from 0 to infinity, sum. We say that A is alternating algebra. Is an alternating algebra if elements of degree 1 have the alternating property. If for any VW in A1, for any V in A1, V times V is equal to 0. So V squared is 0. And so, and therefore, for any V and W in A1, VW times V is minus V times W. Okay. Now let's prove some properties of alternating algebra, and next time I'll talk about the exterior algebra. So which is the most important example of an alternating algebra. Oh, sorry, I forgot. Just say A is also associative. No, A is unito, maybe. Is also unito. It could be known. So the unit is 1 is A0. This is the unit in A0. And usually it's associative, but it's useful to work with non-associative as well, like in cochain spaces. But let's end usually associative. So not associative in discrete spaces. In cochain algebras. So usually in the literature, because people study alternating algebra manifolds, they assume it's associative, but for some of the properties, it's not necessary. Sorry. Remove that. Remove that. The logic for discrete spaces is different. What should I ask? What would
is a requirement for it to be an alternating algebra, or does it follow from it being an alternating algebra?
So it's not usually, it's you always. Well, we require to have a unit. Yeah, it's a useful property. I mean, it's useful property. I think in the literature they assume it's unito. So it's associative, unito, and alternating, and has alternating property. Yes. So and associative. Okay. So let's state some proposition, and next time we will discuss a specific one, the exterior algebra of vectors of a module. But now this is general. So let R be a commutative ring with unity. A, which is direct sum, is unito, is an alternating R-algebra. Yeah, so to give examples of how alternating algebra, I have to talk about the exterior algebra. So I will not give examples today. I'll just prove, or maybe only state properties. And then we have two things. So first, if J is odd number, then and V is in IJ, then I have to assume something, sorry. Okay, sorry, assume that all elements of A, K is I, are linear combinations of products. So for instance, V1 times Vk, where Vi, V1 to Vk are in A1. So any element of degree K can be represented as a sum of things of degree 1. Like any polynomial of degree n is a sum of products of polynomial of degree 1. So in the example I gave two. For example, I gave tensor of the dimension 2 and 3, and that of dimension 3, for example, was something plus something, and both of these additional how they call term that is added. Both of those summands are products of 1 degree elements. Yes, so we have this property. And then if I is odd or J is odd, and V is in ij, V squared is 0. So
Do you mean the tensor products? V1 tensor.
no, we have algebra, so we have multiplication. This is part of the signature of the structure. We have algebra, so we have multiplication given by the definition.
So it's not necessarily a tensor algebra. It's any.
Yeah, any alternating. If so, odd elements to the square are 0. We only assume for 1 degree, but it holds for all of them. So I will not write a formal proof, but the idea is that, well, it's not that easy, so maybe I need to write formal proof next time. But oh, this follows from the next one. Yeah, so this one. So if let ij are in N, I don't know why I wrote this first, because it's a consequence of the, and V is in ij and W is in IA and W is in ij. Then I have then sorry for the language, but then V times W is minus 1 to the power ij of VW, WV. So this is a consequence of this, because if the power is odd, I have that V squared is minus 1 to the second of V squared, minus 1 to the odd power, which is negative. So this, from this follows this. So we have from this. And why is that the case? Yeah, okay, I will show that and we will finish. Sorry for being a little bit late. So proof. So let me call this 1 and this 2. So obviously, 1 follows from 2. 2 when when V equals W. And so minus 1 to y squared is minus 1 when J is odd. And so V squared is minus V squared. Here I assume that 2 is not a divisor of 0. Anyway, there is little detail that I will not mention, but there are rings when you can add things with itself and become 0. But we assume for any x, 2x is not 0. Anyway, that's a detail that we can discard. Now, how to prove 1? To prove 1, consider only monomials. So let's say V is V1 times Vi, and W is W1 times Wj. These are, of course, V1 to Va and W1 to Wj are in A1. Okay. Then we have W times V is W1 Wj times V1 to V I. And so we need to compare this to this times this. And this is counting the number of transpositions to go from this to this. Do you know transposition? When we change two elements. So we need I times j transpositions to go from double V this thing here to the opposite, to V1 Vi and times W1 times Wj. And each transposition changes sign. And each transposition changes sign. And so there we have minus 1 to the power of ij sign changes. And this is what we wanted. Now this is a little bit abstract. Let's write a concrete example of changes and we'll finish. So let's say V is V1 times V2 and W1, W2, W3. Now we start with VW, which is V1 times, or maybe WV. This is W1 times W2, W3, V1, V2. And now we are starting, so this is, we swap this. So this is double minus W1, W2, V1, W3, V2. Swap again, so we take minus 1 to the second power. W1, V1, W2, W3, V2. So we are going here, here, now we are going here. Minus 1 to the third power, V1, W1, W2, W3, V2. And now we start the same walk with V2. Again, one more, V1, so we get this here. W1, W2, V2, W3. W1, V2, W2, W3. And minus 1 to the sixth power, V1, V2, W1, W2, W3. Which is minus 1 to the sixth power of V times W. Is it clear now what I'm doing? Okay. Anyway, let's finish this long lecture.